Welcome back to Beyond Bandwidth, Leviton's podcast series where we dive into network technology's hottest topics. I am your host from Leviton Network Solutions, Roy Chamberlain. This conversation aims the spotlight on AI data centers. In part 4 of our 4-part special edition to this series, Leviton's Mike Connaughton is the host for this discussion as the panel answers questions from the audience.
All right, I'm going to start off with a couple of questions. We'll see where it goes. Generally, I'm going to address a question to somebody, but anybody that wants to answer, please feel free to weigh in. One thing that might be specific to Nick, while you were talking about the power limitations from the grid in the UK, there was a pretty interesting ongoing study done by the Department of Energy in the US. In a nutshell, they look at the forecast and they're saying, basically, even with these, we consider astronomical growth projections, they're not worried. They're saying there's enough power in the U.S. It's just at a local level, there may not be enough power in the region you want. And you mentioned the FLAP-D. To us, that's Northern Virginia. Northern Virginia is going to have an issue. There's just not enough power plants. You're going to want something next year or the year after. It'd be someplace else. Is there similar issues going on in UK or Europe that you're familiar with as far as people just saying, all right, we can't put it in Frankfurt. We're going to have to put this data someplace else just so there's available power to light it up?
The short answer is yes. I mean, that give an example of Norway, actually, where we're about to open another office in sort of southern Norway around sort of the Oslo area and stuff, sort of, in fact, further south than Oslo. I think there's a difference in power between north and south. This is that a consumer would pay a tenfold difference.
No.
And a lot of that is down to the infrastructure to be able to transport the power from one area to another. We don't have that in the UK, and I mean, that's probably an extreme example. It isn't just power generation. It is also being able to transport it. I mean, another example, not perhaps directly related to data centers, but we have a lot of wind in the UK, of course, and they've got a lot of wind turbines in Scotland. And sometimes on windy days, they literally dump the power to ground rather than use it because the interconnects down into England are not sufficient to be able to carry that power through. So there's enormous amounts of work that need doing, I think, all over Europe. And as I say, it's not just power generation, it's the infrastructure as well to carry it.
All right, interesting. Question on the connectivity. Jonathan, Brooke, you both brought up the new small form factor connectors. From Jonathan, I'm looking to you to say, how do you see those new connectors becoming part of the structured cabling designs? Again, specific to AI, I think, because of the density. And Brooke, do you see a point where it gets beyond structured cabling and may become part of the actual transceiver interface? Maybe we'll start with you, Jonathan. How do you see that rolling out?
We have a need for the highest density in our distributors where we're having all the patching for the spine switches and the super spine switches. And when we're designing those, we want to have the patch fields take as little space as possible so we have more space for switches and everything else. And a great place to have these very small form factor connectors are the patch panels at these distributors. So you could implement it in your structured cabling almost right away when they're available from your manufacturers like yours. I would see them be even more useful on the other end, on the server side and the server cabinets, if the transceiver manufacturers started adopting them too, particularly when we're starting to go to the 800 gig and the 1.6 terabyte connections in 2026 when DJ comes out. Then I wouldn't have to go from a patch cord that has the MMC on one end and NPO on the other end. I can just have a patch cord that has the same connector on both ends because, as many of you may know, when you're running a cord with different connectors on each end, you'll very frequently have the installer install the wrong end on the wrong side, and then you have to reinstall the cord. And so it's a big hassle for when you have to have different types of connectors on each end of the cords. I'm really looking forward to being able to use these connectors in the patch panels right away, as soon as they're available, maybe a little bit further when we're seeing them on transceivers.
Yeah, and I'll just add to that. I mean, I think Jonathan said it, the primary deployment for these are going to be in the patch panel to increase the patching density. A little bit further down the road, we may start seeing some of it on the transceivers themselves. And in fact, there's prototypes out there. If you go to OFC and other optical shows, you can see that some of the vendors will display the technology. History has shown that at least so far, that the transceiver manufacturers like to maintain LCs and NPOs on the transceivers themselves. And that probably will be the majority of the volume still, but it's possible to put the small form factors on the transceivers. One of the other areas where you might get just from patch panel straight down into the server, where you have the small form factors on either end, is actually in that co-packaged optics architecture, where if you're bringing that transceiver functionality back into the ASIC, essentially to get it to the faceplate of the switch, all you have is just a very small optical connection on the ASIC itself, but just a few fibers that go out to the faceplate of the switch with the small form factor connectors. And now the switch is really kind of like a patch panel at that point, because it's just a coupler. So then you would have your small form factor on the face of the switch and then up in the patching infrastructure.
Open it. Anybody got any questions from the table out here? Oh, we got one from the panelists. Here we go. We're mixing it up here.
There's a question for Jonathan, actually, to do with very small form factor. So how are TIA looking at the two connectors at the moment? Are they going to be including those two connectors along with LC and MPO, or is there more work to be done first in terms of royalties, availabilities, and so on?
Okay, well, that's a good question. Well, the whole development was held up by the patent dispute, which I think which has been resolved. In terms of these connectors, TIA tends to adopt an IEC standard. So for the connectors that we have, we're sort of waiting for IEC to start work on it, and then we'll adopt the IEC standard. As far as I know, that work hasn't started yet because the 2 fiber versions of the connectors involved in that dispute were sort of held up. And so the work on the array ones has not. But my hope is, and I've been encouraging my colleagues in TIA who work on the fiber side to start working. Mike, you work with 5.6.3, I think is the committee that worked on the connector one.
Dot 13.
13, yeah.
Oh, yes.
3 is my committee.
That'd be an easy way to push it. Take over the committee.
Yeah.
Last week, actually, was our plenary for TIA.
We had new
That was raised last week, was the status of the small form factor connectors in IEC and bringing them over to TIA.
So I'm right about we generally adopt an IEC standard, right?
Yeah, the duplex connectors are the ones that the work had started, it halted, so it's essentially restarted. So I think it's going to be relatively short order that the duplex styles of small form factors will enter into the standards, but the array connectors might be a little runway in front of us before that comes out.
Yeah, so I think in this case, the standards will fall behind the actual implementations of these standards because where manufacturers are already making these very small form factor connectors available, but before the standards are available. My hope is that the standards will keep up. Well, we'll start catching up.
So you talked about NVIDIA, AMD, and Intel, each having their own reference architectures, which are different from each other. There's kind of initial implementations, kind of inconsistent use of structured cabling.
Right.
Do you see the use of structured cabling have an influence on those designs as it becomes more mainstream, as more and more people start to deploy it?
I think when customers deploy them on small deployments, very often they're buying the whole thing as a package, including the switches, the cabinets, the racks, the cabling. And if it's a small deployment, they may just do the whole thing with direct cables, including the connections from the leaves to the spines. But as they grow up and as they see how these things need to be grown past this first little deployment that they've done, they find that they need structured cabling. So most of the ones that we're doing now, where we're doing these second generation deployments, we're doing the leaf, the spine cabling, we're doing all structured, particularly since this 400 to 800 gig jump is just around the corner, right? It's just around the corner. It's going to happen really soon. And then the availability of 800 gig on the same 8 fibers, and again, that's in 2026. That's just next year. So you're going to see that. So 2025, we're going to see 800 gig in all the reference architectures, I think, not just Intel, but in the AMD and the NVIDIA one. And the products are already been announced. And then in 2026, we're going to have 802.3 DJ, which will support on the same 8 fibers, the 800 gig. So you won't need 16 fibers for 800 gig. You only need the 8 that you run 400 gig on now. And then you can run 1.6 terabytes.
So do you see, maybe you were saying that the reference architectures will start becoming similar? I mean, I think back to the reason structured cabling existed was in ancient history, the predecessors of Cisco and Arista today, they all had their own various ways of cabling, and then eventually became, no, this is the way you cable, and this is the way a switch interfaces with it. Do you see that happening with the GPU interfaces?
I think they'll be more accepting of structured cabling, if only because you will start going from small deployments to larger deployments. And for you to implement a larger deployment, you really need structured cabling because you can't have that many volume of cabling in your distributors with individual cables, which just won't physically fit. You can't buy optical fiber trays that big unless you have really tall data centers. Then you have stacks and stacks of trays. And it's really inefficient to run tens of thousands of long cords. And then after your first one, what do you do when you want to upgrade? You have to start pulling out cables at the bottom because they're the old 400 gig ones. And you have your 800 gig ones on top, right? So how am I going to do that without disrupting my environment? So in terms of being able to label things, being able to manage things long-term, troubleshoot stuff, they're going to learn the same lessons that we learned in the 10 megabit. It's just that a lot of the deployments are being done as these one-offs, but now they're going to have to get used to being part of a bigger data center and being managed by the structured cabling people, just like everybody else.
There we got a question on the end of it.
So Jonathan, you talk a lot about the designs you've already worked on. What's the best way, and not just from a manufacturing perspective, anyone that's working with you in a specific deployment can help support you with technical designs in AI architecture?
Well, if you're implementing a reference design, it's actually fairly simple because the reference designs are very, very straightforward. But when we're working with clients that are deploying non-AI things where there are no reference architectures, just knowing what you want to do is really, really helpful. So when we start working with a client, we document our assumptions. What are your assumptions? What are you trying to accomplish? Right? So, and for an AI one, you might say, okay, what am I trying to do now? And how big does this thing need to be? What am I looking for? Do I want to build for just today? Or do I want to build for maybe like a 2, 3, 4, 5 year cycle? For 5 years is almost forever in the AI world, though. So who knows what AI will look like in 5 years. But if you want to design for at least 3 years, you're looking at 800 gig at least, right? Maybe for 2 years, you're looking at 800 gigs. So when I design an infrastructure for that, I have to think that I'm going to have to install enough fiber in my infrastructure, or at minimum, have my pathways and my patch fields designed for the amount of fiber that I need to upgrade to 800 gig if they want to do that in 2025. And if they want to go to 1.6 terabytes in 2026, again, that's another doubling of the fiber, at least from 400 gig that I have today, right? So we're designing all our patch fields so that they can be doubled, all our pathways, all our patch fields. And we're not buying the fiber right now unless they figure that they want to do that upgrade soon, right? And then knowing what the full layout of the floor plan will be. If I'm planning to build, let's say that I'm building a big data center and I know that I'm going to have this many nodes, and I can lay out my data center and plan my pathways and build the distributor big enough for the amount of cabling that I'm going to have in. Like the client that I was working with said that I'm not only do I have this room that I'm working on, Jonathan, but I have another room that I have to connect up to it. I have another room. And I counted the number of fibers. I had 70,000 fibers coming in from that other room into my main distributor. So I have to figure out how am I going to get 70,000 fibers into that main distributor and get enough patch panel space, all the switches. That's a lot of space for a lot of switches and a lot of cabling. So I have to know how much that'll be. And I have to know what sort of switches they're planning to use. Are they going to use InfiniBand from this particular manufacturer? Because they're and I have to, because the number of switches that I require will depend on the port count. Are you familiar with these switches that they're when you're building these non-blocking networks, because half my capacity is up and half my capacity is down, if I'm building my whole network with small switches like 32 port switches, I need a ton of switches to build a non-blocking network. Whereas if I'm using 128 port switches, I need a lot fewer, right?
I led the witness there. That was I manage the technical team. Pete's on my team.
Okay, so you know all these things.
I certainly not to your level, but it helps to have somebody articulate it because it helps us to understand what we need to help support you. So Nick, welcome back to the U.S. again. You talked about power and some of the power issues, and especially recently, our team has seen a significant increase in rear door heat exchangers, but we also know that that's almost a temporary solution with where we're going with heat loads. At least that's the feeling we're getting, is that they're not going to be able to handle the heat loads that we're going to need for the future. Swag, because we don't know what the future will bring us. Where do you think that the power that we're going to be able to cool? Is it going to be immersion? Is it going to be more on the optic side? A little bit of both? Do you see an emerging technology that's kind of coming to the forefront that's maybe at the very infancy?
I think it's got to be immerse. If you fast forward 10 years, think of some of these AI clusters now and the power that they have per rack. I mean, I can only imagine what it's going to be in 10 years' time, and it won't be possible to do it with air. So I think it's got to be, immersed.
Do you feel like that's going to be contained within, because we've seen both styles fully immersed, but we've also seen some early designs, kind of some pie in the sky designs of, immersing within a specific rack unit, if you will, or a switch itself, if you will?
I don't know is the answer. I would imagine that it will depend on the architecture, right? Depend on the configuration. Going back to your original point about the rear door heat exchangers, I mean, there is a feeling by some that it's a sticking plaster, if you like. But I think that, also have to look and say, well, specifically to do with AI, the deployments out there that perhaps need, 50 to 100 kilowatts, it can be an effective way of dealing with it. But in an existing facility where there aren't other options available. So I do think it's a useful product, but probably not the product of the future. There's a lot of other business out there other than, AI clusters. The majority of the world aren't deploying these. I'll probably have to eat my words in 10 years' time, but at the moment, so yeah.
We're not recording this for posterity or anything.
Oh, well, that's good.
No, very, very good. Thank you. And Brooke, kind of the same question around LPOs or co-packaged. Obviously, power is really important, so it kind of makes sense that maybe co-packaged is the way we'll end up. But the initial feeling is that maybe linear is the way we're going to start. Is that kind of what we gathered from your conversation?
Yeah, I think so. I think we're going to see the linear drive optics kind of as the stepping stone to eventually get to co-packaged. I mean, there's already proof, and we've seen it in demonstrations at trade shows and other places that they can, do 800 gig with a linear drive. They're certainly looking at doing 1.6 with those transceivers, and I know I wouldn't be surprised if we hear of NVIDIA and AMD and others, looking towards linear drive optics once they hit to the 1.6 data rate.
I have a question for you, Brooke. Is there, when I go to the co-package optics, that completely eliminates the transceiver, like the AOC type solution, doesn't that?
Yeah, it would.
Yeah,
it would. I mean,
that goes copper. The DAC completely goes away, obviously, because it's copper. But the AOC would disappear as well.
Yeah, and there's also there's challenges with the AOCs as you get into the higher data rates, and you've got the casing of the transceiver on the end of that at 800 gig and the 1.6 terabit. I mean, you've got to be careful of the weight of those transceivers, and if you're trying to pull those across, an overhead tray, right, they become susceptible to damage. And so for the direct connect, in particular, as you get higher and higher in the data rate, just straight up MPO array cords, become much more feasible.
Yeah, it's hard to pull 1,000 AOCs through a conduit, is it?
You just make the conduit big.
That's right.
There is a simple solution.
That's right.
I've got one more question.
yeah,
If I
absolutely.
just sort of put to people. So just thinking about hollow core fiber, and Brooke, you obviously spoke about the big losses. My understanding is that the losses are where you transition from hollow core to normal glass,
Yeah.
and that's the proprietary bit that Luminicity, I believe, provides sort of pigtails, if you like, 2-meter pigtails, and they do that joining themselves. And actually, splicing hollow core to hollow core is relatively straightforward. I think you need a three arc splicer to do it, and obviously glass to glass is simple enough. But I wonder what the future of it is in terms of whether we're going to be able to connectorize hollow core fiber without transitioning to standard glass, or whether you can, there might be a form of AOC where hollow core fiber goes end to end, because those are the big losses. I don't have any of the answers on this, by the way. There were just some thoughts when you were talking about it.
Yeah, and I don't know that there are solutions for that yet. I mean, that's part of, certainly if there were ways to do it, right, it would make it more feasible to put that in the field. Now you still have the cost consideration, and who knows what the loss would be at that point. Maybe it's going to be less than doing that transition. But yeah, we'll have to see what's to come. I think we're years and years down the road before we get to solutions that offer that.
Yeah. I have a question for you, Nick, on the heating piece. Now going to kind of direct to chip, I guess. But with the CDUs, the cooling distribution unit, the ones that are mounted in the racks, that becomes kind of part of how you deploy that. Are you seeing any pushback or concern from the customers saying, all right, we're already running out of rack space, and now we have to add rack space for cooling technology, which traditionally was not in the rack per se? Is that a conversation that's happening in the market?
It's not one really I've come across. I understand what you're saying, though, but I guess the thing is that as you, it probably always comes back to a limitation of power into the facility. So at the point where you're taking out racks that might have been, say, 10 kilowatts, and you're suddenly putting in racks that might be, I don't know, 40, 50, 60, 70, you're not going to be able to take 100 of these old racks and put in 100 of these new ones. There are going to be fewer higher powered racks. There's certainly plenty of people that don't like the idea of putting a CDU in the rack and having water sort of pumped to their servers, but that's here to stay. Maybe it's another one of those sticking plasters. Who knows? For the future, maybe that's just a transition to fully immersed liquid cooling. But yeah, I think that it would be more something that people might push back on if you were building a brand new facility and that were the technology of choice. Then people might be looking at it and they might say, well, do we want a CDU in a rack, or should we put those somewhere else?
And you mentioned it there. It came up a couple of times in different answers about what we're talking about now is AI data centers and the cooling and the power requirements of them. Not every data center is an AI data center, and certainly not even every data center, even AI data center, is a back-end network.
Yeah.
What's your sense of, fast forward 5 years, and we're not recording, we will not hold this against you in the future, whatever your answer may be. But what's your sense in 5 years' time? Like, what's the percentage of the market that's AI data centers as opposed to traditional data centers, and in whatever form you think of, as square footage, as far as power usage, as far as dollars, and that's a question for everybody. What's if you're in Las Vegas making a bet, where would you lay your money?
I think I'd heard that people are thinking that most of the training will be done in the cloud. And that you mainly have what our inference service. You have training where you're training an AI to perform a certain task, and that requires the big GPU networks and a lot of power and cooling. And then there's the inference part where the trained AI is doing a task, and you need less power for those. And you even theoretically can do AI on a regular computer or even on your phone, right? So those are doing inference. And it depends on what you define as that. And that might be, I think that'll be really common. And I'm kind of excited. We've been hearing a lot of news about DeepSeek, right? That's kind of like the big news that tanked all the AI stocks, the GPU manufacturers. But I know that there's issues with that in terms of it being open source, and the news about how they created all their models, whether or not they use these big GPU farms that didn't. Like, I heard that they had a few thousand NVIDIA GPUs that they may or may not have gotten past all these regulations to train their models. But the idea that we have new AI software that can do what we used to do, but maybe more efficiently, and it being open source, I think is good for the industry. So one is that, sure, I'm still going to need 8 GPU servers, right? But now maybe the growth won't map up so much, right? So I don't have to, that growth rate, I would still be able to use on my older GPUs. I still be able to do some pretty decent stuff. The other thing is that if I don't need as much processing capacity to do really serious AI, maybe that'll open up the GPU training to more organizations. I don't have to go to Google or Meta or some other place to train those in the cloud. I can train those in my data center, in my space, and maybe I'll have a smaller area where I'm doing my training, but that opens that up for more people because it's more efficient, right? And it being open source means too that I'm not dependent on OpenAI or whatever with their systems. I can use an open source AI package and have that all trained and managed by me, and that's all mine. So I think that the whole idea that we may have AI that's more efficient and open is a good thing for the industry. And it scares some people, I know, but I think that in general, I think it's good for the industry. It opens it up for more organizations to use, to have more control of, and to do it more efficiently. I didn't answer your question, but
I like the answer. I mean, basically what you're describing to me is structured cabling. I mean, there was a time when people fought it, and that's not good. Right. I don't want to do it that way. But ultimately, when basically the industry agrees, everybody benefits. Everybody kind of figures out their own way to make the widget, but it's got to fit into a box in a certain way, and then the world kind of opens up that way.
The more it's opened up to more organizations to use, the more I think it's good that we have structured cabling standards for AI rather than these GPU clusters only being managed by these big cloud providers that anybody can deploy them in their data centers and get some reasonably good work done with more efficient servers.
Any other opinions on the AI versus traditional data center future?
Maybe I could tack on to that and a little bit. We've heard in the past pushback on structured cabling vis-a-vis latency, which those of us in the cabling industry kind of shake our heads and go, we understand insertion loss and lost budgets. Why the noise in the background about latency and structured cabling when it's not necessarily a distance issue?
Right. Yeah, it's not. Actually, we had the discussion between a client of ours and one of the major GPU manufacturers. And their initial position was, you don't want to use structured cabling. You want to use direct run patch cords because it has lower latency. And essentially the clients were smart. They said, nah, the latency that I lose through a connector is extremely, extremely small. It won't be even noticeable, right? And there is slightly less delay when I'm going from like between an AOC and a transceiver and a cord, but it's not so much that it's really going to affect things substantially. You know, we're deploying big networks and we're using structured cabling. We're not using AOCs except for the leaf to the server side, right? So I think that, and if you go to any cloud service provider, you know, with the big networks, there's no way with the volume that they're doing. If I'm building a data center with 50,000 GPUs in it, it's not going to be 50,000. You're not going to do that with AOCs. You just can't handle that volume, right? There's not enough space to get that many cords in one distributor.
And if I could another follow-up, when we're talking about the next gen of the servers now having, say, 16 GPUs or even more, so now it's 72 GPUs per rack. To me, that kind of drives that we're now going to top a rack for the leaf switch because of the number of ports that will be needed right in that rack. So the server to leaf cord, whatever that is that going to move to the back plane of that chassis?
Well, the thing is that like with NVIDIA architecture, we have 32, the scalable units have 32 nodes, each node having 8 GPUs. You have 8 switches to do that. And they specify what they call a rail optimized configuration. Port 1 on switch 1, port 2 on switch 2, port 3 on switch 2. On every one of the 32 servers on a rail optimized configuration, I have 8 leaf switches, 32 servers. Port 1 through 8 goes to switch 1 through 8. The problem with top of rack is that I have switch 1 maybe on top of rack 1, switch 2 on top of rack 2, 3 on top of rack 3, and so on. But I have to cross racks, right? Do you see the problem? So it's not really top of rack, it's top of the module, maybe. If like a right, I might be able to do all this in 4 racks, right? Depending on how I cool this thing, which is really my thing. Like we're like the one I'm working on now. We're doing air. Actually, we're doing we're doing a liquid immersed cooled one and an air cooled one. On the air cooled one, we have about 30 to 32 kW per cabinet, 35 per cabinet, and a pod is, maybe like 6 racks, right? So you end up with, from the first rack to the 6th rack, you end up with a really, really long cord, if that's the way you want to do that, right? Yeah, so it's sort of top of rack, but it's sort of something else, right? And if you look at the NVIDIA architecture, I think they actually have dedicated cabinets for doing all the switches in the middle of the row. So they solve that problem by putting in the middle of the row. I kind of like the top of rack thing, and we do the top of rack with the in-band management and the storage, because you can have a 32 port switch serving like a half of a pod, because you don't do that rail optimized thing with the storage and the in-band management networks, right? Yeah, so you can use top of rack for that, but the GPU network, because of that, the rail optimized configuration that you have to do, the middle of the row thing sort of works better.
Very good.
Yeah.
Just wanted to make a general observation really about sort of the point-to-point versus sort of structured cabling. Most of my time I spent working for installers, and say that the best advocates for structured cabling are people that have done point-to-point. And also the best advocates for the cross-connect model, right, switch port replication, are people that have done interconnect. Those are the people that when it goes wrong, that they then look at it and go, this is how it should be. So I think, what everyone's saying today is, these small deployments that don't need to be expanded will probably stay with point-to-point, but the larger ones need to have structured cabling. And the people that approve that point to us will be the people that will do it point-to-point, and then people go, oh, we can't do this again.
I have one other question for you, Nick, if nobody else wants to throw one in here. I think in one of your drawings up there, you were referencing kind of the traditional airflow coming from underfloor, from a raised floor. But then kind of the newer data centers, hot aisle containment and so on, tend to be on slabs. One of the big questions, especially around liquid cooling, any liquid cooling, but especially immersion cooling, is weight limits. Do you see that kind of changing significantly, the impact of raised floors versus slabs, or raised floors kind of going to go by the wayside and everything will be a slab because of loading? Or do you think there'll be kind of a mix? Do you think it's going to be engineered solution in there somewhere?
Yeah, it's an interesting point. So a lot of the existing data centers with raised floor, for example, if they use things like rear door heat exchangers, they will often bring the manifolds, the pipework underfloor. It's quite a good place to sort of put it. But I have also seen it where it's just an additional service that's run overhead. I mean, it can get really, really busy overhead, some of the pathways and things. I mean, thinking about one of the hyperscalers, I think they had 6 trays just for data stuff. And then they had buzz bars on the inside of the hot aisle. And if you were to add to that pipework for rear door heat exchangers or to feed CDUs for, DTC, I mean, it would get, seriously busy. I think a lot of raised floors, there are limitations to the amount that they can, that they can support. I can remember doing, when I worked for that professional services outfit, one of the things that we were asked to deal with was back in the days of V blocks. And I think some people had wheeled in some pre-configured cabs into data centers, and they'd gone through the floor in some cases. And one of the things we were tasked with was, assessing a floor, which is a pretty difficult job to do, actually. I won't bore you with why, but for static and dynamic loads and things. And so a lot of raised floors would not be able to support huge numbers of certainly immersed liquid cooling tanks and things. I mean, definitely not. Although, the advantages to hide the pipe work are clear. But there are raised floor manufacturers like Birkvik that also do suspended ceilings similar to sort of Tate, where you can get very, very high weight loadings but still raised floors. But
from the cabling world, one of the things we think about in kind of liquid cooling generally is, whether it's rear door heat exchangers or direct to chip, the actual interaction with the cable kind of doesn't exist. So we're saying, okay, but there's still you're fighting for space, especially in a cabinet environment where it has to enter the cabinet, especially if it's overhead. Now there's a limited amount of space. It's not just rack units of space. It's kind of area of space to exit some overhead tray and enter into the space. So it's one of those things that nobody really had to worry about before. Now, but it's becoming a thing. That plumbing is, you got to think about plumbing access into your racks and cabinets.
I mean, a lot of the things that you see within, just talking about cabling design, within data centers is, you'll often see a very simplistic design of multiple trays, usually all aligned. But, how do you spill out of those? What order should they be in? Where do they enter the cabinet? That stuff really needs thinking about, and often it's not designed in. Mock-ups in those scenarios are absolutely essential to see exactly how everything works. And very often it doesn't work the way that people intend first time round.
Yeah.
So add into that, and then add in, say pipe works to feed rear door heat exchangers. It's going to get, seriously busy.
Yeah.
Seriously busy.
Any other questions from the audience?
I do have a question for you, Nick. I was in the data center last week, not AI. It's a legacy data center. It's an older one that they're looking to replace the raised floor and a lot of their systems. And there was a whole team of people, and there was a lot of discussion. And one of the biggest discussions was on, the refrigerants or the liquid that's being used. Do you see any potential breakthroughs that might prolong, doors and direct cooling that's looking in the industry right now?
I don't know a lot about the coolants used. I know a bit about the different models in terms of where things like rear door heat exchangers get their get the liquid from, whether it's a sort of a low pressure system from a local CDU or pump from sort of further away. But that isn't really related to what the coolant is made from and whether it's environmentally friendly and how long it lasts for and what the effect is on the equipment. I don't know if anyone else can answer that question. I'm afraid I don't know the answer.
Yeah, those were some of the things they talked about too, the environmental impact, things like that. But I just wasn't sure, if liquids were, in development that will transfer that heat more effectively than anything that's around today.
Well, certainly a lot of the petrochemical companies are coming up with I think it's Castrol, Shell, possibly others, right, that come up with the dielectric liquids used for immersed cooling. So I don't know whether that might be something that they're looking into. And obviously one of the arguments with those, even with the the non-synthetic ones, are that they have a very long lifespan, and therefore it's not quite the same as sticking it in a car and firing out the end of the exhaust pipe as a one shot go. So So yeah, I don't know the answer, but that's an interesting question. Yeah, I think I'll look into that.
Yeah, thank you.
I kind of think that I agree that immersion is probably our longer term future, but as a cabling person, immersion creates all kinds of complexities for me. One is that with the optical fiber connectors, the liquid can get between the connectors. So we're finding that optical fiber connectors, like if I immerse a transceiver and the connectors inside the liquid, I could run into some reliability problems because the liquid could get in between the connector, right? I have heard that some AOCs are having the same problem, that unless the AOC is specifically designed for immersion, I might also have the same problem with the liquid getting in there. I know that the copper ones generally work okay, but in general, even for all the types of cables, anytime I have a new immersion fluid, I have to test compatibility between that immersion fluid and the cabling components. They have the connectors, the cable jackets, and everything to make sure that I don't have any issues with the jackets deteriorating in whatever fluid I'm using. So I think it's an exciting area, but my preference is not to have it in the liquid, though I think that eventually we have to deal with that issue one way or the other. But every time I have a new type of fluid that is the Wonder immersion fluid, then I have to go, okay, now what did this Wonder fluid do to my cable, right?
Yeah.
Yeah. So, I mean, I'd say from a closing perspective, it's exciting. I've heard that a few times. I mean, it's confusing. There's a lot of questions. That's kind of what gets you out of bed in the morning. You got to go fix a problem, and there's lots of problems out there, lots of opportunities to come up with a new solution. So, all right. I appreciate everybody's time. Thank you, everybody, for participating, especially the panelists, Jonathan, Nick, Brooke. Thank you for your time and expertise.
Yeah, thanks for having us.
Yeah, thanks a lot. Enjoy the rest of the show, guys.
All right.
Beyond Bandwidth is a podcast series produced by Leviton Network Solutions. For more information on the topics we talked about today, as well as other enterprise or data center network infrastructure content, or to check out all available episodes of Beyond Bandwidth, visit us on the web at leviton.com/beyondbandwidth, or wherever you normally listen to podcasts. If you enjoyed this episode, we'd appreciate you leaving an honest review in your podcast application. Along with word of mouth, leaving a review will help others find our show. I'm Roy Chamberlain, and this was Beyond Bandwidth. Until next time.